So today we have Preshanth Jagannathan visiting us from NREO. So Preshanth did his PhD in Calgary, University of Calgary. When he was doing his PhD at the University of Calgary with Ross Taylor, Ross moved to UCT, so he followed his supervisor to UCT, and then you did an REU in?
No, I did a Reba fellow.
Rever fellow at NREO, and he's been at NREO
ever since, yeah.
For many years. So today he's going to talk about radio astronomy.
Okay.
This.
The other one. The other half. Yeah, it's perfect. Thank you. Okay, hi. So for UCT, just for context, it's University of Cape Town in South Africa. So if you haven't been, it's a great city. I can recommend that you visit. If you choose to live there, it's at your own peril. So radio interferometry at scale. I know this is largely not a radio audience, so stop me at any time if I'm saying something that doesn't make sense. I promise to keep all the picture slides in the first 3 or 4 slides, and so if you're here for the pretty pictures, it will be done by slide 4, and you can leave, right? So just so you know. All right. So I work at NREO in Socorro, which is where we run the Very Large Array. And if you want context for what the Very Large Array is, I usually tell people it's the telescope in contact. Nowadays, I tell people it's the telescope in pluribus. But it's usually the telescope that gets blown up in some sci-fi movie. But it's a Terminator salvation, if you're wondering. There are many more such examples where people like to blow up the VLA. We like to use it. So the VLA is made up of 27 antennas. It's in the high plains in San Agustin. It's at about 7,000 feet above sea level. It's a really nice high desert. If you haven't visited, you should come see us. We have, and it also is. It was built in. It was conceived in the 70s. It was commissioned by 1980, around the time I was being born. So it's kind of old now. We are hoping that very soon we will upgrade this and we'll go to the next generation of the VLA. And as astronomers do, we are very creative at naming things. It's very large, and it's a telescope array, so it's a very large array. So what do you think the next generation will be? It'll be the next generation very large array. So we called it ngVLA, right? So that's what we're proposing for. So somebody was asking me earlier when I was meeting them, what do you actually see in radio? That's a great question. The only part you see in radio is this red over here. It's usually the jets. So all I want to point out is the scale of the things that you see. This is Centaurus A. It's a classical radio galaxy in the sense that it has a supermassive black hole at the center, spewing huge jets. This is typically the kind of radio galaxy that you will see with a radio telescope. So to form a complete picture of what this galaxy is actually doing, you have to look at it in pretty much every wavelength. Yes, sir.
You mentioned this is all you see in your radio wavelength.
Yeah.
Is that because this object that we see visibly is not emitting radio signal? Or
no, it's emitting radio signal, but your eyes can't see it, right? Your eyes don't see radio, so you don't see it.
We agree there.
Yeah, so that is why you don't see it. Otherwise, you would see the whole picture, right? If you had, say, the same eyesight coverage as some of these crazy animals, an axolotl, perhaps.
The point there is this a universal statement? We only see this much.
It is a universal statement in the sense that you see mostly gas spewing out of black holes in terms of radio galaxies. Okay. Yes.
That picture that you have, entirely with radio different wavelengths?
No. So this is visible light. This is X-ray at the center that you see the super bright regions, which are the highest energies. Then you come down, and if you want to see the dust in the central regions, that's what a lot of people over here do. It's infrared. And further down, as Rayleigh follows, everything goes to radio to die, right? So it's the lowest energies are in radio. So we pretty much see everything, right? Anything that is remotely warm, we see it. Okay, so you can also see things like supernova remnants. The red part, again, is the radio. NASA likes to give us the red colors, so I'm just showing you a bunch of NASA images. You also see supernova remnants. The reason I showed you this is SN1006. It's got you see all these kinds of shocks around the edges of the bubbles. That's what lights up in radio, for example. You can also see the galactic center, which is pretty much obscured in every other every other wavelength band excepting the radio, because optical depth goes as wavelength, and our wavelengths are very long, so we just get to go through most of the dust and anything that's obscuring it. So we get to see close to the center of the galaxy. That's Sagittarius star at the center. That's the supermassive black hole at the heart of our galaxy. All these filaments and stuff that you see, they're all real. Some of these are supernova remnants on the sides. These are all bubbles that you see, these old ancient stars that have exploded. These are all kind of things that light up. This is a picture taken with MeerKAT telescope down in South Africa. That's where my boss went to work on. And this is it's a nice thing to look at. And so what kind of processes actually emit in radio? So typically you have thermal processes, you have synchrotron and also free and maser type emissions. So we see a lot of different masers, water, ammonia, different types of masers we see. So because we also are sensitive to magnetic fields, because for any of these emissions to happen, you have electrons going around magnetic fields. So we are sensitive to those magnetic fields themselves. And finally, if there are gas kinematics, also you can figure out spectral behavior by looking at different spectral lines. So how does interferometry actually work? It's just a standard Young's double slit experiment. This is a physics department. I'm sure all of you've done this at some point. All that's happening is that you have the same signal that's received by two different telescopes, and if you cross correlate them, you will end up with a fringe. That's it. It's the same kind of fringes that you see in a Young's double slit experiment. But what do we care? The most important thing is that as you move the telescopes apart, you end up getting more and more resolution. It's the same kind of thing that you're interested in your television, right? You want the best picture quality. You want the highest resolution, and you also want all the colors and all the vivid stuff that you see. So that comes from having more telescopes. So if you want an ideal interferometer, we'd ideally like to fill the aperture plane to about many hundreds of kilometers worth of metal, but nobody's going to let us do that. So what instead we do is we take up we take up two of these pairs, and we cross correlate these values, and then we look at what's going on there. I'll tell you a bit more about it.
What's the time resolution of data?
I'll get to it. I'm getting to it. Just bear with me a few more slides. So the theorem that tells us that what we're seeing is essentially called the Van-Cittert-Zernike theorem, which just links the brightness in the sky to a bunch of recorded voltages, or in this case visibilities. So each baseline samples one of these values, and it does this as a function of a frequency and a time. So that is, if you notice, this is only a spatial Fourier transform. There is no mention of time here. There's no mention of time in this equation explicitly. It comes implicitly in the coordinates, and I'll show you a little bit more about it. So what do we actually end up doing at the back end of a radio interferometer is that we have a sky. We see the sky. We usually have a low noise amplifier. The amplifier takes a signal. We use a down converter, and then we down convert the signal. Then we sample it with an ADC. You're roughly looking at about 10 gigasamples. That's roughly about 80 gigabytes per second per antenna, gigabits per second per antenna. That gets shoved into a correlator, which is just doing a Fourier transform and add, because there's a finite bandwidth over there, and we're trying to recover the bandwidth. So that ends up with 2K channels roughly, let's say, and you have 351 baselines, because the VLA we have 27 antennas, so NC2. And then you will end up, we have 4 different polarizations. We're sensitive to I, Q, U, and D, all the polarizations of light. So this roughly translates to this at the center, you're roughly looking at 2.2 terabits a second. And that, if you haven't worked with that kind of data, it is a lot of data, and you have to keep up with it at any given time, because if your correlator stops working, then nothing, you get no data products besides that. So you're roughly looking at 23 megabytes a second, or roughly about 83 gigabytes an hour, and about a petabyte a year, approximately. So this is what the VLA has been dealing with. We've been dealing with a petabyte a year since 2011, and now, yes, sir.
What are these channels?
So these are frequency channels. So different frequencies. Let's say you were observing from 1 to 2 gigahertz in bandwidth. So it's sampled in say half a megahertz or 1 megahertz resolution. So there are so from here to here is your signal chain, and we have contaminants entering different parts of the signal chain. And so because we are not the only people in the sky, right? So we have a big problem with the new set of satellites that people are launching all the time. This is just 10,000 satellites, right? If you have 10,000 satellites at any given time at the VLA in a single beam that any part of the sky we're looking at, we have three different satellites passing through it at any given time. So this is the field of view is roughly about depends on the frequencies. At 1 gigahertz is roughly about 45 arc minutes. Yeah. So in that field of view, you have roughly 3 of these going around. So remember, that's 45 arc minutes is the main lobe of the antenna. So you have side lobes, and our gain is really high. We are tuned to capture very faint signals. To give you an idea of how faint a signal we're looking at. So there was a satellite that was launched called Voyager in the 1970s. It has the same its transmitter has the same power as that of your cell phone, and we just found it for NASA like 2 years ago when it had just left the solar system, and that means we can see your cell phone out in space outside our solar system. So and at the same time we're trying to catch all the really faint signals going on, right? So it's a false dichotomy. We're looking at something super bright, and we have to deal with this. So how do we deal with it? So some pre-processing has to go on. I'm interested in that. This is called RFI mitigation or radio frequency interference. That's what RFI stands for. So there are different ways. So one would ideally like to remove this signal before it goes into the correlator, because once you correlate, it's in your data forever. So we'd like to get rid of it before it gets into your data. So there are different people who've been using a lot of machine learning techniques to try new stuff. So this was a paper that got from out of one of the national labs. I forget which one, but Solly1Check, they actually tried to see if they can use a variational autoencoder to try to figure out the incoming signal form and subtract the signal form. So, but it's kind of limited, and it fails. So I have a student who's in UCT, and we actually worked on a similar technique to see if we can do any better. So this is their method on the left. What you're essentially trying to do is this. So if you have a satellite drifting through your beam, you get a blip, and the blip is a lot of power, and that power goes up, and this is one of the 10. This is like say 20 samples out of the 10 giga samples that we are sampling per second. So you have to get rid of these 10 samples. You have to find these 10 samples to get rid of them fast enough before you average down, because all the 10 giga samples end up becoming 1 second of data, because we average up in the end to get signal noise.
You would ideally be able to record everything, and
yeah.
then you would have processing.
Yeah.
That would be the best. Or?
That would, if ideally, yeah, I would.
So the problem is it's impossible.
It is absolutely impossible. I mean, you can't even store the correlated data, because that's already in petabytes. Imagine if you had 2.2 terabits that you had to save at any given time. A standard hard drive that you have will be done in 10 seconds, right? So it's kind of it's a little moot. So we can't do that. So what we do is we try to deal with it either at the ADC before the data streams in, whether we can do something near real time. So this is a near real time approach. We're actually going to test this out in the field next month. Yes, sir.
And the problem we are trying to address that pertains to this artificial
Yeah.
satellites is that they obscure your source, or satellites are sending some data at the same frequency.
It's a downlink. The downlink is the same frequency. So their up and downlinks are on the same frequency. So we're actually staring at a booming bright source beaming down. So you can't see the sky. It's like looking at the sun. Actually worse than the sun.
And you can talk to the people who send the satellites.
No, so we talked to SpaceX. This is actually not coming from our main lobe. This is coming from the side lobe. What SpaceX did was we created a system where we share data with them. So every time an antenna actually goes over the VLA, they steer the beam away. So we are doing beam steering, but this is just for side lobe interactions. Side lobe interactions are still killing us. So for example, okay, so we did a simple units. Units are very fast. The reason for a unit is because it's simple, it's stupid, and I like stupid and simple. And so we do a unit because it's tiny quantities of data that you can actually pump into an onboard chip somewhere, into an RF sock, and then just run it on an RF sock. Oh yeah, it's a form of neural network that's a common architecture for a neural network, which follows a U shape. So it starts with a large number of layers at the top, goes to a bunch of small convolutional layers, and then comes back to a large number of layers to store your data. So the shape looks like a U unit. Not very creative, but it works.
Like a neural net.
Yeah, it's a neural net. It's a neural net, but it's shaped like a U because of some stackings. So this is if you use a neural net kind of approach, then we're able to sort of get rid of all the data. So what sky for us when we record a noise is purely Gaussian. So we're trying to recover a signal that should look like pure Gaussians. So we recover a signal that we cannot tell the difference from in terms of any kind of standardized algorithmic Gaussian test that we have. But that doesn't mean that we keep data fidelity. We have to see how good or how bad we're performing. So this is work in progress, but this is the kind of stuff that we're trying to address and look at. So the other place it also fails is, for example, if you have 2 satellites or 3 satellites drifting through, then the other approach just totally keels over, and the unit seems to still work. So which is good because it's able to identify a signal form. All right. So okay, what happens if you cannot get rid of your data beforehand, and it's actually made it into your actual observation, and it gets averaged up? Then the only means by which we can get rid of data is we can look at time and frequency, and then say, hey, statistically threshold some values and say this is good data, this is good noise. Anything that's above some threshold value, say 5 or 6, some n sigma, we just clip and throw it away. Just mark it as bad data and we discard it. So the kind of data loss we're looking at is over 30 to 40% in some bands, and it's only getting worse. So if it gets any worse, there'll be a point where it's not worth looking at the sky anymore. But we're not there yet. Well, I will be jumping up and down if that was coming, but it's not quite there yet. I'm not very alarmist. Okay, so if that's the case, so this is the standard approach. The other way that I was looking at is the thing that anytime you look at a time frequency plot, let me show you one. This is Gaussian noise. Everything that doesn't look like dark blue is RFI. Your eye can instantly tell you every single pixel that's RFI. So why can't? Oh, that's great. Sorry, that's an excellent point. This is frequency going from here to here, but it's actually channels of the frequency. This is actually data going from 1 to 2 gigahertz. It's channeled. That's 2K channels over there, 2048, and that's arrival time. So that's 0 time over there, and then these are all time steps. Okay, these are something like 512 iterations in time. So it's 512 by 248, 2048. So
no angular resolution. Just one channel.
This is just for one baseline. This is the data that you get post correlation. You get time frequency. Yeah, you get time and frequency all the time. And so this is the amplitude. So our signal's buried here. We have to make images. So I'll show you how we make those images. But we have to get rid of these things first. If you don't get rid of this, I can't calibrate my data. Yes, sir.
What's the unit for the time?
The unit for time is in seconds.
But do you expect anything to change in seconds?
No, not the sky, but I expect the local environment, the RFI environment to change a lot. So that's why we sample as much as data rates would permit. Okay, so once you do that kind of sampling, you're trying to get rid of these bad data. Your eye can instantly see some of this is bad. So the simplest way to do it in terms of a machine learning approach is to say, if your eye can see it, you can segment it. So that's what we did. I had an undergrad a couple of years ago work with me just to show you what you see what we are trying to get at. But if you notice, we miss some stuff. I don't try to hide what we don't get. For example, this. So as it's not perfect, but it's already better than whatever is nominally the state of the art. And this is a single shot. It's one pass. It's very quick. It runs on GPUs. It's a big win. So this is another way of looking at it. So now that I have all my data, ultimately for astronomy, we ideally would like to make some images. We want to see what's in the images, and that's where our science is. So how does that work for an interferometer? An interferometer is essentially sampling your aperture. So every point that you have on a given time or frequency is just one dot over there for any given baseline. So if you notice here, there are many axes changing. For two antennas, this looks like a fringe. As you add more antennas, you fill up the number of dots. Your image gets better. And as you add more and more data, in this case, the Earth does it for you, because the L, U, and M that you saw are changed as a function of the Earth rotating. So this is called the Earth rotation synthesis. So because the Earth rotates, it fills up this aperture plane for us. Yeah. So in the right, this is the sky, right? So this is actually whatever you look up in the sky. So we call it LM and N. But on this side, this is the Fourier domain of that, and we call it UV and W. Just some alphabets that we picked. We like those alphabets.
Like originally, you have like a few spots. What is one spot?
One spot is a Young's double slit fringe for that baseline in the sky, and in that time and in that frequency. So as you can either fill this up by adding more frequencies, or you can fill this up by adding more time, and that's what we do. So that's antennas. You see, if you increase the number of antennas, the number of baselines increases NC2, right? So the more antennas, more baselines. That's one way. The other way, see, that's the antennas increasing. Then it's 2 hours. Then you wait in time. Then that's 4 hours. Then we're adding more frequencies. We're adding 3 more frequencies, 4 more frequencies. It's called.
Maybe just like a clarifying question. So
yeah.
Every antenna you have.
Yeah.
It's a dish.
Yes. Every antenna is a dish.
Does it matter if it's a dish or?
No, it could just be 2 wires in the middle of nowhere. Yes, and people have done that. I want a dish because of. Oh, so what's the wavelength? Okay, so we typically operate from 1 to 50 gigahertz, and our dish size is about 25 meters. So we have a few lambda across, right? So at least a few lambda. In our case, 25. It's 12, right? Because it's about a meter, half a meter, say. So this is essentially aperture synthesis. So you can, as you have more time, if you can add more time and frequency, you end up filling the aperture. You end up making better images. All right.
As you said,
yeah.
Time goes on, Earth rotates. So
yeah.
The spot that you saw first is no longer
the same spot.
Digitally account for that.
Yeah, I get a different UVW because the LM and are different.
So you update everything.
Yes. So that's why we have to constantly sample. And then after you get that, so this is where your data sits. Then it becomes a standard sparse imaging problem. We're going from a Fourier domain to a domain where to the sky, and our aperture is relatively sparsely sampled, and we have to reconstruct an image out of it. There are many ways to do it. Radio astronomy converges on this idea of major minor cycles. The idea being that fast Fourier transform is faster than doing a direct Fourier transform, and we have a lot of data. DFT is not an option, so you have to do an FFT. So which means you have to take data which is not on a regular grid and put it on a regular grid and make that image, right? So that's what you're doing. That's step number 1. That step is called gridding, and then we take an inverse Fourier transform to get to the sky, and it looks like that because it has the sampling function built into it. And you have to remove the sampling function. This is an image domain operation. It's called deconvolution, where we remove the sampling function. I'll talk about this in a little bit later. So let's just focus on the gridding step for now. So it's sparse. We want to take this IFFT, so we want to grid our data. Now I showed you that we have a lot of data. So imagine if you have to grid 80 gigabytes of data to make a single image, right? So that's pretty common for us. How do we do that? How do we accomplish that? So typically there's this idea. Imagine this is the sky follows an ellipse, right? So the rotation follows an ellipse for us. So these are the actual true samples. We want to take these true samples and then we want to interpolate them onto a regular grid. And this is our regular grid. We plop a convolution kernel at the center of those images. We multiply with that point, and then we read out the values of those locations. We add them up for every single overlap. All right. So there is none over here, but for these it does, and so on. So this is a single track and a plopped convolution kernel. This is We call it convolutional resampling. You can decide what your kernel is going to be. The kernel decides the support, which is basically the number of pixels that spans over here. So for this circle, the support for this particular convolution kernel, the support is 3, spanning 3 in any axis. All right. So this is convolutional gridding. This convolutional gridding is what is commonly known as NUFFT. It's popularized as NUFFT. If you're an applied math person, you know it as an NUFFT. But radio astronomers have been doing this for about 50 years. It's been copied, and MRI and medical imaging folks have also borrowed this from us. So if when you're in doubt, there are many modern libraries. There's FinUFFT. There's now a CUDA version of that, but it's still not as fast as the one that we use. That's what we've done. That's what I spend most of my time doing, is to come up with fast gridding algorithms to get over this data deluge. To give you an idea of how crazy the data rates can get, this is the VLA, and this is the MeerKAT that was built like a few years ago, and it's currently taking data. It has 64 telescopes, and it averages about 16.6 petabytes a year. That's the data rate. And this telescope is being constructed right now, and when it's finished, it is supposed to produce 150 petabytes a year, roughly. And we are proposing to build the ngVLA, which is going to do 300 petabytes a year. To give you an idea of what 300 petabytes is, it's more data than the entire internet every year, right? We have more every year. We have more data than the entire internet put together every year. There's no way you can store that.
And when will it be in operation?
So this one is proposal stage. We got approval from the national academies, so it's being put up as a line item whenever it gets approved. I don't know. With the current administration, I'm not holding my breath. But for this one, this is a joint European. Many countries are pulling the monies together to make that. That's the construction's underway. So it's supposed to finish by 2030. So I'm talking about problems we have here and problems we have here. I don't even want to talk about the problems we have here. So the pitch I'm making is that if you cannot fix your problem today, you cannot fix this. And to fix this, you rethink your algorithms at every stage. You have to rethink how you deal with your data at every stage. The biggest constraint is your data. It's not what is the best algorithm. It's just the fastest matters more. Something that can fit in RAM matters more. So you have to start working within constraints rather than solving an ideal problem. Okay, so we decided that this was a problem, and that 80% of all compute that we do goes into the gridding step. So it's the biggest nail that we had to solve. So we said, okay, let's try to move this to the GPU, and let's do this fast, because gridding is embarrassingly parallel. You have a bunch of data, you just send it to a gridder, just add it to the same location. It should be really, really fast. So we worked on a GPU accelerated gridder, which does it about 160 times faster than what CASA does. So if you have a tiny laptop GPU, you can grid 80 gigabytes of data in about 6 minutes on a laptop GPU. Now suddenly the problem is a little bit more tractable. You can think about making images. So that's where we want to go to. So if I can think about making an image of 80 gigabytes right away, it opens up new possibilities. By the way, all that code is public. We develop in public. You can see our mistakes. You can see our failures. It's always on GitHub. All right. So we also try to do additional algorithms. If you're interested in talking about different kinds of direction-dependent algorithms, this is my bread and butter. So I'm happy to talk about those, but I have a lot more things to show you, so I'm just going to keep going on. All right, so then we said, okay, how do we show that it actually works? So we said, okay, let's take the hardest data set that we could think of at the VLA, which was the Hubble Ultra Deep Field. I took this as a graduate student, and then I went to SDSC. I don't know if you know about SDSC is the San Diego supercomputer. They have large memory nodes, large different types of nodes. They have a 14-day wall clock time. That means that you can run a job, it cannot exceed 14 days. In 14 days, I cannot even finish making the FFT done for this 1.7 terabytes on standard CPU-based parallel ways. I spent a good 1 year trying this, and then I said, okay, I can't keep this up. So then I revisited this once we could do this on GPUs. And then we used this idea where they have high throughput computing, because you have a lot of data. You don't care when it's processed, but you want it done. So we shipped our data from NRAO to this center called the High Throughput Center, CHTC. CHTC then packages the data, sends it to available GPUs anywhere in the country. And then they crunch it in their local machines and then they bring it back to us. And then we take it all back and then we make an image. So this allows us to deal with 1.7 terabytes, which to be processed in roughly 8 hours. It was 1 day because we had to run it a few times. So it's in about 8 hours we were done. So this leads to an image which is about 1 microjansky per beam. A microjansky is 10 to the minus 26 watts per meter squared per steradian. So it's like kind of really, really, really faint values. So to give you an idea, this is 10 to the minus 32 of that. So because a Jansky is 10 to the minus 26. So this leads to one of the deepest images that radio images ever made. This is the Hubble Ultra Deep Field. Unfortunately, it renders terribly on the screen. It looks great on the laptop. Every single dot that you see here is a galaxy that's far away, right? Typical redshift, the median redshift in this is 5. So median redshift in this image. These guys are very nearby, the big ones, but every other dot's kind of far. Typically star-forming galaxies, typically stuff that you don't actually make images with, in radio at least.
Before you go,
yeah.
From that image, what do you learn?
So what we learned is, for example, it gave us a census of let's say how these galaxies sort of evolve. There's a redshift range in period of time. We were able to cross correlate with other optical data, for example, and we could say whether these are star-forming galaxies, what is the magnetic field properties of those galaxies, stuff like that.
Just from one image that you showed the dots,
yeah.
you could tell all that?
By comparing it with other wavelengths.
So
by comparing it with other wavelengths. Yeah, so those exist already. For example, like the Hubble makes the Hubble Ultra Deep Field available to everybody, right? So it's the same idea. Okay, so deconvolution. So I showed you those initial images. They all have our sampling kernel. You have to remove the sampling kernel from all of your images. It's a process called deconvolution because the sky is convolved by your sampling function. It's a simple convolution equation. So because the interferometer only samples some of the spatial frequencies, not all of them, but you want to reconstruct an image which is smooth and samples everything, you're trying to fill in missing spaces, which also adds to your problem. So it's an inverse problem that's hard because of that. Because your emission has many different scales, many different actual physical scales, and you're only sampling a few of those.
You mean it's only 27 points?
Only 27 points, but let's say your emission continuously spans, say, 5 arc minutes, and I have a sampling function that terminates everything above, say, 1 arc minute, because the interferometer has no sensitivity beyond that. Then how do I reconstruct 5 arc minutes worth of emission? That's a problem.
Sampling only at 27.
I can only sample at those points, yeah, but 351 samples because only pairs. Okay, so we came up with an algorithm called clean. Clean is really stupid in the sense that it goes to the brightest spot on the map. It says, okay, I'm going to subtract out what I think is the PSF or the point spread function multiplied with some gain factor, and that gain factor was, let's say, 0.1 or some number like that, and then you just subtract some flux from there, and you keep going until you hit a point where you are not sure that any more fluxes you're subtracting is confusing with any other source or the side lobes of the PSF. So you keep going. So you end up with a bunch of delta functions in various pixels, and that's your standard clean algorithm. So you have this is M87, you have M87, which it gets reconstructed as a bunch of points, which is not how the sky actually looks like. So when you actually compute a residual, it looks terrible. So this is maximum entropy. You can think of it in a Bayesian way. You can say I'm trying to fit my model to my sky, and you will end up with something that looks like an MEM model, and which works fairly well for larger scales, but still not great. So there's another one that says multi-scale clean, which says, okay, hey, I can figure out what the scales are in my image using some techniques, and if I use those scales, I don't have to use one PSF. I can use many PSFs. That's multi-scale clean. It does better, but it's not great. But you can auto-discover what the values are by using some more math. It finds out that you can a smooth representation of the sky is better with a smooth basis. So the basis we use here is a Gaussian basis. So if you can reconstruct the sky as varying with Gaussians, you can compute the widths on the fly. You can do that. It's computationally more intensive. This takes about 10x the time it takes this guy to finish, but it's much better. But again, you only deploy this if your science needs it. Not always, not all the time.
This is an image that the last.
Yeah, this is a residual. You've subtracted. This is your. This is your model. This is your actual image that you made. This is essentially what comes out, and this is what the residual looks like. So that's one way of looking at it. There's another. So that is, if you can find a basis, if you're able to find a mathematical basis, I should be able to learn a basis, because you can find one. If there exists a basis that represents something smoothly, I should be able to teach that basis to a computer and be able to access that basis fast. Again, neural networks. But there are two different ways by which you can look at it. So this is essentially the equation that we're solving. But so this came out in this very crazy paper from Zeiler and Fergus in 2014, where they showed that if you look at what a neural network actually learns and look at all the intervening values inside, and you try to pass data through the weights, you actually see that the weights look like filters. They actually look like crazy filters. It looks like convex filters, concave filters, which one might not conceive of, because we're trying to think of convex optimization. But nonetheless, they're filters, and these are learned representations, and this is from a convolutional neural network. So I said, okay, if that's the case, why not we just do this on some representative galaxies? So there are some people have been kind enough, in this case, Porter and Scaife, who've actually gathered a bunch of galaxies which they think represent all the varieties of different radio galaxies that exist. So okay, fine, let's learn on this model, and then see how well we can represent radio data from that. Okay, so this is what the machine learned. I'm trying to show you that the basis. This is the basis that it's going to use to reconstruct the sky. This basis does not look like a human basis. You don't see points, dots. You don't see things that actually are connected shapes of any kind. But this is what the machine is learning. There are two different methods. This is a convolutional method, and that one is just saying, okay, here's a pixel patch. Learn all the various kinds of pixel patches that truly exist. And so that's what it learned. And with that, here's the original. This is data that it's never seen. I'm trying to reconstruct the data using the learned representation. If you ask it to represent it using this patched learning over here, it does sort of okay. But if you actually look at the residuals are fairly tiny. So it's learning a little bit of the noise, which is kind of bad, because we're not constraining it in any fashion, or not smoothing it in any fashion. So it's actually learning some bits of the noise, which is why you get to see all the edges. But when you teach it with the convolutional dictionary, it learns that your data is smooth. And this is what the residuals look like. So it's actually modeling sources that it's never seen extremely well just by learning on some other set of random radio galaxies. It has never seen these. So I said, okay, that is radio galaxies it's never seen. How about a supernova remnant, which is not a radio galaxy? Doesn't look like any other radio galaxy. So this is particularly a nice supernova, because this is the supernova in which there's a pulsar. It's the first pulsar ever detected. This is the one that Jocelyn Bell looked at. It's got a nice pulsar in the center. It's personally a favorite of mine. It's a nice looking supernova. So if you reconstruct this is the original. And I showed you that patch learning, even that really crappy learning produces flat residuals. Same over here. There's absolutely nothing. So which means there is a learned basis that we can use to reconstruct pretty much anything in the sky, and really, really, really fast. This does it at 1/100th the time it takes for me to deploy one of those complex algorithms. So the win is the speed. The win is the speed. All right. So remember, I only trained it on FR1, FR2s. If you don't know what those are, that's fine. It's different types of radio galaxies. And so all I'm trying to show you is that it's not memorizing, it's learning a representation. Okay, so I showed you images. Now that's deconvolution. Once you're able to deconvolve, make better images, you finish your looping, you make nice looking images. What do you do with that? Personally, I work in, I like to look at Faraday rotation. Faraday rotation is essentially saying that, okay, your incoming electric field vector gets altered by the line of sight magnetic field in the presence of some ionized plasma, and it gets rotated by some angle. So let's say whatever angle it's getting rotated by, you should be able to derotate it and recover the true signal. So this, sorry, this didn't render properly. That's supposed to say capital P. So every time you see a box in the next few slides, replace it with a capital P. Capital P is in complex linear polarization. So it uses the Q and U, the two different polarizations of light, and so this rotation can be seen by looking at signals in Q and U. So that's one way to look at it. And the other way to look at it is there's been a lot of really fun theoretical work that's been done on this, starting by Burns in 1966. This is and Sokolov in 1998. These are absolutely excellent papers. If you decide that you want to look at magnetic fields in the sky, I would highly recommend reading these. So there are different ways you can reconstruct the intervening plasma. You can think of it as thin sheets, thick sheets. You can have emission from the back end or throughout the plasma. Compute a bunch of integrals. You'll end up with nice looking formulae which sort of represent the various cases: turbulent screens, not turbulent screens. But all of these means that we actually have a form that we want to apply to the signal that we are seeing to see whether that's what the intervening plasma is doing to us, right? So those are called depolarization models. But in radio astronomy, we came up with this idea that, hey, that integral looks, so this is the integral P of lambda square. If you think of it in terms of some weights, looks essentially like a Fourier kernel again. We radio interferometers love Fourier transforms, so if anything looks like a Fourier transform, we don't jump on it. This looks like a Fourier transform. So they said, okay, let's do a Fourier transform and sort of define something called a Faraday depth and see whether we can resolve the various plasmas that are between us and the final source through that. It works. It's fast. It's called RM synthesis, but it's not quite as accurate as forward modeling with known set of plasma values. If you say, hey, I think it's a Burns slab, it has one component, it has two components. If you a priori try to fit a model, that model, nothing beats that in terms of accuracy. We did a compare against standard methods. It was not me. It was done by Larry Rodnick out of University of Minnesota, and they concluded that, hey, QU fitting is better, and I agree with them. But the problem with QU fitting was, if you try to do this in a proper Bayesian way, you're trying to fit a model to your data, it ends up taking something like 2 or 3 minutes per pixel, and we're talking gigapixel images, right? So 2 or 3 minutes per pixel for a gigapixel image, you're going to wait forever, which is why the adoption is kind of slow. So this year I had a student who's a Fulbright fellow from India who showed up and said, hey, I'm trying to do this for clusters of radio galaxies. I want to do it fast. How do I do this? So around 2020, there's a lot of fun advances that's going on in computer science. There's a computer science group came up with this idea that if you can simulate anything, you should be able to teach a network the mapping between the probabilities of the data to the outcome. It's not learning the physics, it's learning the physics. It's not trying to learn the physics itself, it's trying to learn the probability distributions of your input parameters to the output. So it's a mapping between the two probabilities, which means that every time I ask it to give me a fit to the data, it gives me a fit. It actually gives me a Bayesian fit with some priors and tells me what the errors are. So we used a particular method called neural posterior estimation. There are a lot of other fun ones. I don't know if you've heard of. There are neural flows to look at. You can think of writing a differential equation in time that connects the two distributions, for example. There are a lot of fun math ways you can do this in. And if you're interested, look it up. These are really, really good. If you have any kind of model that you're actually trying to map parameters set of A to parameter set of B, there are some really nice ways you can do it with neural networks now, fast ways, and still stay deterministic, right? So the key that I'm pushing for is that whatever we're doing should be deterministic, should be measurable. You need to be able to see what's inside. If you cannot build intuition, if you cannot build confidence, you should not do it. All right, so then we did that and we said, okay, so the state of the art right now is this repo called RM tools. And so we try to recover, this is the simulated values, that's the true values, that's in black. and these dashed lines are our recovery from our SPI. So this is the true value, the true value of the parameters that we put in. This is the parameter estimation. So our estimate is off, but it's still okay. But the current ARM tools is terrible, huh?
But your estimate is biased. It's still off.
It is off. It's off, but it's off, but it's fast, and it's in the ballpark. It is better than what the analytical estimate is. It is because we're learning the prize. It's actually turning out to be better than than doing a Fourier transform inverse and computing what things look like. So it is, and to give you an idea of how fast we're doing it, we went from 2 to 3 minutes per pixel to 30 milliseconds.
You're doing fast, but getting bad results.
I'm fast, but getting bad results is fine because I can iterate through my loop, and at every iteration, my gradient converges to a better value. It's a looping algorithm. I will take loops. I will take an approximate answer over no answer, right? So yeah, no, it is bad. I'm not even hiding it. I could have shown you a better looking plot. I mean, that's not the point. The point is the speed. All right, so we recovered them pretty well. If you try to apply it to this is a real galaxy cluster. I forget what it's called. I think this is the toothbrush. Yeah, this one is the toothbrush. It's supposed to have some emission here, but it's too faint. You can't get the RM values for that. This is called a toothbrush because, yeah, it looks like a toothbrush.
Not in that picture.
Yeah. Well, it has these filaments that come out of this at the end, but it's not in rotation measure. We don't have enough signal. Yeah. So this is an L band, and this is an L band version. This is from RM synthesis. This is what we get. It tells you how off we are. I'm off by a few tens of RMs, but I can do this in 10 seconds for that, and I'll take that because for a gigapixel image, it's a win. Because the previous one took me days to get to, right? So it's not worth it. So to give you an estimate, this is the true value. This is how close we are. There are some error bars here that don't render on this, but they're on my screen. They're over here. My error bars are large on the fit, or that our estimate tells you because it tries to recreate the scatter. You saw the error estimates. Our error estimates were larger. So remember, we are trying to fit. We're still giving you parameter estimates, and we're still giving you errors on those parameters. We're not just giving you a black box value that you have to swallow. All right, and at least here, hopefully there's that's how large my errors are. And this is the reconstructed value, and that's the standard QU fitting value. So you can see this is nice and clean. We are noisier, but we are more truthful. We are more representative. So there's ambiguity in the data that analytical methods hide. We are trying not to do that. We're saying that, hey, this is my best estimate, and it is error prone and it is noisy, but that's the truth rather than tell you that everything is hunky-dory. I don't like the hunky-dory. All right, so the next thing that we're doing is we're trying to extend this to, say, IQUV, all the other polarizations, so that we can jointly image large cubes. He's underway. We should be done. This paper is being written up. It should be out in a couple of days. So this is the case that I'm trying to make here is that, remember, I want speed, and because there's too much data, and I cannot deal with this much data if you wait to crunch them. I cannot store them. So you have to really push for speed. All this work was done in collaboration with these three people that I want to particularly highlight. Arpan, who worked with me on this SPI stuff, is a wonderful graduate student. He's going to go work for the SKA, the big telescope, starting in November. And this is Gerard Deal. He's an undergrad of mine. He's just going to grad school this year. He worked with me on the flagging data stuff initially. This is Walter Silema, is another PhD student of mine. I showed you where we were doing pre-correlation subtraction, and that's Walter Silema, and Sri Krishna Shekhar, who works with me, who's a collaborator of mine. So none of this would be possible without these three people, at least. If you take away nothing from this, I want you to remember that better algorithms, not more compute, solves your problem, but you have to make your algorithms fit to your necessities, your computational needs, and how to get through what is the reality, which is that you have to get through things really, really fast. So I showed you that you have to address every stage of the data pipeline. So you have to start from pre-processing. You have to address that. You have to address get rid of bad data. You have to address imaging. How can I grid my data fast because I'm dealing with terabytes and terabytes of data? Then I show you how to get rid of deconvolution fast, and again using some new techniques that are machine learned. And finally, in the post-processing stage, we're saying, okay, hey, we can actually do post-processing really, really fast in really, really automated fashion, so that you end up only dealing with science. If somebody asks me what is going on in this image, I don't have to wait 2 years to tell you that, because that's currently what's happening. I would like to be able to tell you that tomorrow or right away, or for you to be able to find out on your own on the archive, right? So that's the goal. So that's where we're going towards. So thank you.
So when you're processing certain chunks of data,
yeah,
that's pretty large. That's sitting on something like a RAM, or
yeah, it is sitting on RAM, but we optimize for throughput. So the RAM touching is very, very low, because it turns out that GPUs can crunch data faster than you can load data off disk and get it into the GPU. So we have other problems. So our current bottleneck, we're at 160x, but 160x is suboptimal. We're using the GPU at 15%. If I want to use 100% of the GPU, then I need to get more data in much faster. That's what I'm working on next.
in terms of tuning the algorithm, you're basically improving the complexity with n square root of n and so on.
Yeah, in some sense, yes. In some sense. Not always the case, but yeah, most of the times, yeah.
Questions for Preshanth?
Or critiques. I'm happy if you tell me this is all you're full of shit. We'll take that. It's okay.
I have a question. So for
Yeah.
the math clean, how significantly faster than self-cleaning?
Good question. I don't know the answer yet. It's literally work we're doing right now. But again, it's public, it's available, but I don't know that answer yet. That's why there is no paper attached to it as yet.
Yeah.
Everywhere else, I said there's going to be it's publishable work, but that one I'm literally just it's me, so nobody else is doing that. So it'll take a while. Yeah.
And then deciding which neural network to use.
Yeah. Yeah. So you have to choose. You have to understand what mapping works best. You have to understand the physical parameters on both sides. Then you pick a network that satisfies both your endpoints. So you will end up with some form of. So typical neural networks, you find that a unit is a standard one. You can very trivially define one. The shapes are all custom. It's not like predefined. I'm not borrowing somebody else's unit. But the algorithm is simple, right? The idea is simple. So, and I like simple. And which means that the weights that it produces is a small number. And I control the number of parameters that go in the unit, and that's a big win, because people tend to just make the units arbitrarily large. The other thing I want to make the case for is that that's a terrible idea, because that's the number of free parameters you're fitting to. More parameters is not always the answer. So we start with very, very small neural networks. Some things that, like I was talking about, and if you don't know what an RF sock is, it's just basically it's a radio frequency system on chip. It's like a tiny chip that runs my down conversion or incoming voltages, and that's a tiny Linux computer. It's a tiny Linux computer. It's very tiny, and that on which I can host a tiny neural network through which this data is being piped, and has to do that very, 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 very fast and without failing, because the VLA never stops taking data. So we shut down for 2 days in a year, well, Thanksgiving and Christmas. So we're on. So the data is always flowing. We're always looking at some part of the sky.
Another question. So for like simple parallel case,
Yeah.
Where RM synthesis is reliable.
Yeah.
Have you compared dual SDI with RM synthesis?
Yeah, still many times faster.
Faster and in terms of
Accuracy, yeah. In terms of accuracy, it's actually like within tiny error values.
It's similar to RM synthesis.
It is it's very similar to RM synthesis in terms of like Faraday simple quantities, but if it's more complexity means crazier outputs.
Any other questions for Preshanth?
I'm here tomorrow if you still want to ask me more.
What makes these GPUs so good at certain types of calculations?
So it's a different architecture, right? So the CPU architecture is the chips are general purpose. They're supposed to do a lot of different types of instruction sets. But GPUs are a fixed set of instruction sets. The instructions are basically what hardware values that you can do, like what operations you can do on the chip. And those are restricted. There are a finite number and the clocks run slower, but there are more of them. You can pack more of these onto a single chip. So which means that you gain more compute as long as your problem can be distributed. And that's the win. And that's the win in GPUs versus CPUs. They're actually worse at computer cores than your standard computer cores. There's just more of them.
It's what I would say is more maybe a question or a statement. From what I'm hearing,
Yeah.
that you have an embarrassment of riches because you have too many data, you don't know what to do with it.
Yeah.
Where I want to go from here is how do you convince future machine makers or observatory builders that, oh, bring me not 300 petabytes per year or per day or whatever number you said, but more. They'll say, hey, you already have too much data. So where is the emphasis? How to get meaningful information from the data we're getting, or to get more data?
No, I'm with you. The goal is get more meaningful information out of the data. Humans cannot think of 200 terabytes. You want to think of a single image. You want to see what's going on there. You want to look at the physics that's going on in a galaxy. I think that's what an astronomer or somebody at a university should be focusing on. But we're not there yet. Right now, what we give you is I give you raw data from my telescope. I tell you here's a post-processing script you can run on it. Go run it. And but an astronomer, but an average university person cannot do that. So you're a source start, but you want to think about the science. You shouldn't have to think about the data. That should be my job. It should be the prerogative of the observatory. And I think we're not doing enough. And it's a pitch that we should do more. And it'll only be heard if there's enough astronomers or enough people going back and telling NSF or making the case to NRAO that, hey, we want better data. We want final end products. We want this. I'm trying to build consensus that you should ask for better stuff because I think you're owed it. And I think we can do better. That's the case that we're making.
But what I'm getting from what you showed us is some results that you could get today, but it may not be the correct thing.
No. I'm just saying it's approximate. I'm just not saying it's wrong. I would not show you something that's wrong, but it's in the ballpark, right? So
and that's good enough.
I don't think you've met many astronomers, sir, because I think if it's because if it's within because our distant estimates are terrible.
So you've got all these terabytes of petabytes of data and plausible.
Possible, yeah.
Okay. I'm satisfied.
Yes, sir.
Early in the talk, you showed us the Starlink constellation. If that was to be turned off for a year, how much less effort would you have?
Excellent question.
How much less cost?
How much less cost in terms of?
In all ways
in all the ways that we're doing stuff. I mean, it's cost saving is not very much because it's most of what we're doing is in compute. So and the compute costs are in electricity and the initial setup cost. But it'll make my life significantly easier. I can also get 20% more bandwidth. I can make better images. I can get you unreachable spectral lines that we cannot access right now. For example. So quantify how much easier my life would be. It's hard to say because it's also 5G cell towers. They just turned on one right next to the VLA. That was so much so that we actually had to tune our bandwidths upwards to avoid the cell frequencies. We just did that 2 weeks ago. I don't know if anybody's had a VLA proposal at the low frequencies. You'd have gotten an email saying, "Hey, we had this unfortunate cell tower that turned up at 2.1 gigahertz." So if that was where your science was, tough luck. If it's not, please tune upwards. We had to send that email out. We just lost 20% of bandwidth that way.
What would happen if you could persuade Starlink to send you all the data that's there?
Oh, that's not gonna work because that's not our. Yeah, and it's proprietary stuff. We talk to them, and it's proprietary information. They don't want to share their encryption. They don't want to share what the data downlink strategies are. They don't even want to tell me what the signal form looks like. You know why I had to use machine learning to subtract that? Because if they told me what the signal form was, I can analytically subtract it. I don't need to guess it, but they will not tell you that. And they are protected by the FCC. The FCC should be working for the people. It works for Starlink, amongst others. But
Would that cure your problem as easily as turning it off?
yeah. Because yes. The answer is yes.
Anyway, so Preshanth is here tomorrow as well. So if you'd like to chat with him, I encourage you to reach out to him. If you're interested in NRAO positions or machine learning,
I have to make the case. Okay, there are grad students here, and if you're an undergraduate student, please consider applying for REUs. Derod there, who was here, he was an REU student of mine. He's excellent. I really like working with undergrads, but you should be willing to try something crazy and out there. So if you want an easy problem, not me. But if you want something weird, yes. Right. So that's my pitch. Weird, come to me for sure.